Hello everybody and welcome to today's XP Live webinar. My name is Nicole Highlander and I'm the Marketing Manager here at the XP Solutions Portland office. Today's webinar is going to discuss how to leverage xpstorm while preparing the existing conditions and design conditions models for a simple project. So if that's the topic you're here for, then you're in the right place. For those of you who may not be as familiar with XP Solutions, we have a long history of providing high-performing software solutions. Our intention is to make sure that in your work you can model with confidence, and this means that we strive to provide excellent customer service and support, and that we offer continuing education opportunities like these for engineers in our industry. Today's presenter is Matt Anderson, our Storm and Flood Products Manager. Matt joined XP in December of 2016 and comes with very valuable experience, especially for today's webinars. He spent 6 years with Autodesk and most recently as a product manager. He spent over 16 years as a private engineering consultant, and over the past decade, he's been involved in improving the workflows and technology that engineers use to study and design civil infrastructure and water resources. Thank you everybody for joining us. We appreciate it, and welcome, Matt.
Thanks, Nicole. Thank you for joining today's webinar. As Nicole indicated, we're going to talk about, or I'm going to present a little bit about a project and talk about how to use xpstorm to evaluate the existing floodplain limits, and then how to explore the resulting proposed floodplain limits within the context of a design. And in this case, it'll be a culvert underneath a road, but we want to explore how to build that existing conditions model. We want to explore really that two-dimensional analysis of that floodplain. In many cases, we might use a tool like HY8 or HackRAS to analyze the culvert itself, but in this case, we want to focus on the floodplain. We're going to leverage the scenario manager to look at 3 different scenarios for this culvert replacement project, and then how do we incorporate that into possibly new floodplain maps in our production environment. Before I get too far into the presentation, Nicole, I want to see if we can launch that poll and just ask the question to our audience here. When you're modeling that flood project, what type of design project are you working on? Are you working on a proposed land development project? Are you a municipal engineer who's looking at conveyance, making the pipes bigger, building a bigger ditch? Or are you looking at municipal, you need to kind of reduce that peak flow, and we're going to look at storage. Are you a transportation engineer looking at rehabilitation, which I think will be the topic for this presentation? Or are you doing, new transportation projects, brand spanking new roads, which is kind of a little bit of what this project that we'll go through is. So cool, we've got some people here voting. Thank you, Nicole.
Sure, we're about halfway there, say.
Mm-hmm.
And as soon as we get a full vote here, we'll show the results so everybody can see what everybody else is doing.
Yep. Yeah, this is these results are interesting. A little different than this morning, but generally in the same vein.
Okay, 5, 4, 3, 2, 1. There we go.
Cool. So we got about almost 38% of you who deal with proposed land development projects, which, well, I might take that into consideration doing as we plan our future webinars. And I think, Nicole, correct me if I'm wrong, but I think at the end there'll be a opportunity for comments, and would appreciate any comments on what you might want to see presented in one of these hourly webinars in the future. So, all right, cool. Thank you, Nicole. let's kind of step into the presentation at this moment. All right, so our project, as I kind of indicated, we were going to look at a transportation project. And in this case, it is a road project that we're adding lanes. So the existing road and the existing culvert has one lane in each direction, and it's going to turn to become a divided highway. And we want to take a look at determining the existing flooding extents upstream of this culvert. We're going to look at ultimately some culvert design options. This is where we'll leverage the scenario builder, or scenario manager, not builder. And we'll identify changes in the elevation of the floodplain. Most of it upstream of the culvert, but there's going to be some effects downstream that we'll want to take a look at. So really, where do we want to begin? Well, with any good job, we want to kind of start with a template. In this template, we want to actually store those elements that will be repeatable. In this case, this is a roadway transportation project. Maybe it's for a county. Maybe it is for a state department of transportation. Something in this region, or maybe a district, that contains elements that we want to continually see, so we don't have to reinvent the wheel or recreate the wheel time and time again. So we want to build a template, maybe how we present link and nodes in our model, or we want to include specific global data from our global, or populate our global database. Things like our 2D land use elements. Possibly if we're doing hydrology, which we're not in this webinar, we could use standard rainfall and put those design storms or design rainfall events within the global database. Maybe if you're going to use just a standard 1D xpstorm and build links and nodes that represent our manholes, our inlets, our underground pipes, as well as our surface cross-sections, maybe we'd include some standard roadway cross-sections to be used within the multi-links. But one of the other elements that we want to show you today is how data import mapping can be included. And we've talked with a couple of customers where this is their standard practice, allowing linking of an Excel spreadsheet to be included in their template. And all they've got to do is put the template in the right spot, and away they go. The next step in an existing conditions model is primarily our terrain surface. And in this case, we've got a terrain surface in a design application. And that design application could be AutoCAD Civil 3D. It could be Bentley Inroads and MicroStation. It could be Carlson. Probably could be something on BriskCAD. But in this case, the work has been already done for us. So we have a terrain surface, a TIN, and we want to get that into xpstorm. In this case, we're going to leverage LandXML. And LandXML is going to provide us that direct conversion of the digital terrain model or surface in our design model directly in xpstorm, and we'll do that face for face of that triangular model. I want to just contrast that to some of the other elements within xpstorm, which is things like DTM Builder, which will do triangulation, but it may not preserve triangulation if you were to import that same XYZ file in AutoCAD from xpstorm. So we're going to use LandXML to make sure that any break lines, any terrain surfaces or edits that have occurred within that triangular surface in, for example, Civil 3D, is maintained and brought into xpstorm. Well, our next element would be, our next set of elements really are our network elements. LandXML, I prefer this primarily because the applications that I'm used to, I came from Autodesk. land XML is a standard method of transforming that information within our design model to other design model or other applications like xpstorm. Even though Easter has just passed, I'm not an eggs in one basket type of guy. So I like to create land XML files that contain my surface as an individual file, another one as another land XML file for each pipe network. Yes, land XML can accept all of these, but I prefer to do this one at a time so that I can make sure that elements that I want and displays that I want, I can walk through those. Land XML is not our only method of importing nodes and links. We can use GIS data, geospatial data points that represent node elements or lines. Now, this can be simple. I think the first couple of tutorials for xpstorm and xpswim, GIS information is pretty sparse. I don't think we import any rims, elevations, things like that. It's just location data. So geospatial will import the geometry as well as any data that gets mapped. But what I want to demonstrate today is the use of the database. And the database can be as simple as a Microsoft Excel table, or it could be complex as a SQLite server, an Oracle database, something that requires an ODBC database connection. And I don't want to demonstrate that today. We're going to use Excel. Excel is pretty simple. So xpstorm is the application I'm going to use today. xpswim, everything that I do in here could be done with xpswim because they share the same storm flooding engines. There are some variations, and you can talk to your account manager about those. But in this case, I want to start and create a template, or start from a template. So I'm going to place in my webinar model directory our design file. I'll just call that webinar afternoon. I think I spelled it wrong, but it's okay. In this case, you'll notice I created a webinar start template this morning. This is a little bit different than our standard templates that you can download from the Resource Center, but it's real easy. I started with that US template. I added some elements that I thought were necessary for this presentation, saved it out as a template, and now I can begin to do some work. So let's go very quickly take a look at what's in this template. Now, in this template, we have some global data. In our global database, we have a whole ton of information that is available. But what's pertinent for today is we have our 2D land use categories. And these 2D land uses are the records that provide information about what that land use is about. In this case, this land use is a roughness. It's a Manning's roughness. We're going to use this in our flooding model to represent the road. So we've named it road. We've given it a description. I don't think that's the right description. I didn't bother changing that. But this is something that we can, customizable for you. We can always, if we wanted to, we could indicate infiltration properties associated with this land use. It's a road and we don't need any at this point. But we can also do rain on grid. Again, we're not going to get into hydrology in this webinar, but it is there and it is available. We could also include rainfall. Let me step up in here. Rainfall. So in this case, this model, this template contains a number of SCS rainfall types. Pretty generic set of numbers, not specific to this element. But as I said, we're not going to run some hydrology today. One of the other elements that we did that I did prepare for this model was the ability to import that Microsoft Excel information. So on the file, import, export, on the second item, the import, export, external databases, I built two mappings to an Excel file called Culvert Design. And this Microsoft Excel file has 4 tabs in it, 2 for the existing, 2 for the proposed. But in this case, I'm only going to show you the existing elements. And we can look at those mappings for the head walls just by selecting the mapping and look at what they are going to bring in. And what we've done is we've mapped this table to node elements. We've used the node name, which is one of the headers within the table for the node name. And in this case, I have an X and a Y. Maybe we took this off of Civil 3D's Prospector, where we have the X and Y coordinates for our structures, and pasted this into our Excel table. One of the other elements that we did do is we pasted both a ground surface as well as an invert for each of these elements, and we've mapped them to the elements within xpstorm. Kind of if we look at, or if we consider, doing this hard work once, this Excel spreadsheet and our xpstorm, all of this data can be maintained and stored in our template. And there's a lot of values, so we can probably begin to actually build a template that represents most of our conditions. I'm not going to change those, but we can take a look also at the culvert, and we have name and we have really what it's connected to up and down, as well as the number of barrels. In this case, we have 1 barrel. But both of these provide, give me a second, didn't want to leave that dialog box. Both of these provide us that ability to very quickly import all of this information. We get confirmation that's read. It will not show until we close this, which I'll go ahead and do. And I'll zoom to the location, and there's our up and down head walls. But we can come back to that, and I can import our culverts pretty quickly. Close that. So now we have really our network elements. If I right mouse click and look at the conduit profile, we have some of this information. So we've got rim for our upstream, invert for our upstream, same for the down. We have just the logical connections for our pipes. We'll fix that later. The other element for our existing modeling is the ability to import our land XML surface. If we come back up here and import land XML, I can scroll to my project location, and I have an existing .xml, which is my land XML file, which I'll go ahead and select and open, and we'll give it a second or two to import this, and it'll zoom to the extents here, hopefully while I am talking. Give it a second or two, and we should be coming. So there we are. Now we have our terrain surface imported. Now it does come up and show as a result in a filled color, and that may be something we want to look at and modify these to represent something that we're a little bit more accustomed to looking at. And I'll change these display properties to change or display only a 10 and 2 contour interval. So we'll make our every 10 feet a major every 2 will be a minor. And we can very quickly display that. We have the ability to add labels and the like to the dialog, but I don't want to clutter this for the webinar. Let me go ahead and zoom in. Wrong icon. I'll zoom in a little bit closer. Just to show you how to check our triangulation, we're going to select and add a layer, and we'll just call that tin. On that tin layer, we're going to use a polygon. I'm just going to clip an area here in the middle of my model so you can kind of see what that land XML, how the triangles of the land XML have been imported into xpswim or xpstorm in that case. So we have really the beginnings of our model here. Obviously our diameter is a little loose. We can look at that and tweak that. Go ahead and turn this off. We have elements. I don't want to be doing that. Look at my manhole. So I'm just going to double click on that, my head wall here. We have spill crest. We have an invert. Because I'm going to utilize XP2D, I'm going to go ahead and link this invert to 2D. Okay. So my pipe is going to be connected ultimately to the ground surface. And this ground surface here is all linked. So we would do this for the 2 manholes and the 2 structures and add that type of elements. Now we talked a little bit about land uses. So we have a land use for roads. And before I digitize that, I kind of want to load that CAD file in as a background. I'm going to load in the new road design. And that's going to take us to the extents. And we kind of see here in yellow, it's a little difficult to see, that we have now really what is going to become our southbound lanes as well as our northbound lanes. So if I can come back to my roads, yes, if we have polygons that represent these land uses, we can import them. But I want to just select that, and I will just, again, use our polygon command and very quickly put in my rectangle that represents my roads. Take a little bit more care when you're modeling yours than I just demonstrated by snapping to 3 points. But hopefully to give you that idea of how easy it is to build an existing conditions flood model. So once we have all of that, we're pretty well ready to go. Before I do that, let me switch back. I want to switch back to my presentation. In many cases, if we were doing this in HECRAS, for example, we would probably be looking at identifying, either importing or digitizing the thalweg, the center of channel. Likely defining where those tops of banks are, where the top of bank is from the surface. Maybe our surveyor didn't pick it up. Maybe it's part of an aerial photography. We'd also define cross-sections. And those cross-sections are our interpretation of how water will flow at a uniform elevation. Water is always going to flow perpendicular to that. And then based on those cross-sections, we're going to be applying roughnesses, to that cross-section. So our model is really only good there at those cross-sections. We're interpolating between each set of cross-sections. And we're forcing water in that 1D model, to go from cross-section to cross-section. We don't give it that opportunity to, take a right-hand turn between those 2 cross-sections very easily unless we've defined some other elements. But with 2D, we're allowed to explore how all of that occurs. the basic elements, kind of as we've shown earlier, we need that terrain, that DTM, whether you import a bunch of points into xpstorm or you use other software to create that tin, xpstorm can read that. We then build any one-dimensional element networks. In this case, this is a culvert. We could, in very specific instances where we know, we could do a 1D channel. But in this case, we're going to utilize the storm. We're going to let the water flow over the surface. We're also going to utilize land use polygons or the absence of polygons to represent roughness. And we'll use the default settings for our 2D model to represent a roughness for the entire model, except for those elements that we've specifically defined, so that you don't have to make a grass element and make a polygon that contains everything but the roads. And then the next element would be our boundary conditions. How does water flow into our model? How does it flow out of the model? And that is typically defined with a line and then some hydrographs or a head boundary at the downstream end. Again, very simple workflow. So let's switch back to xpstorm. And I actually have a completed model that we'll kind of explore here. It takes about 10 minutes to run, and we're kind of at the bottom of the hour at the moment, so I don't want to waste your time watching a progress bar go by. So as you can kind of see here, it looks very similar to what I just built. Okay. And we'll step through this process. We'll look here. There's our road polygon. And again, this has information. There's our Manning's roughness. And we're going to ultimately use shrubbery as our everything else. And in this case, it's got a much higher roughness value. And that's established in our configuration we'll get to here in a minute. Again, we have, let me zoom out a little or zoom in. We have our head walls. And if I look here at the conduit profile, I've actually added up and downstream inverts as well as a diameter of 2 feet. Roughly 65 feet long, so we've got a good slope to this culvert pipe. If we look at our water surface profile, we'll look at just the existing conditions in this case. So I'll expand this out. So this is really the digitization of that Thalweg. So this is what our channel looks like. We have water comes in here, and it looks like we have an area of storage upstream of the existing road, and it flows downstream. So how does this model perform? Actually, before I get to the performance of that, let's look at our boundary conditions. Zoom out, sorry. So in this case, we have a head boundary at our downstream condition. And in this case, I could see just based on the contours that there appears to be a channel here. We know from maintenance and some records that in the most recent storm that we had measured, we know that this road overtopped. We don't have much beyond that, but we just know that water went over the road. The question that we wanted to make sure that we handle is, where is that water going? So at this point, I've put a head boundary at the top here, as well as one down here. I'm going to edit the data. So I've looked at this information, and I just put, a time condition for 6 hours, and the elevation roughly at this edge, a little bit short of the edge, so I don't make any big errors, but enough that XP2D will calculate normal depth as it reaches this line. And there's a similar condition at this other element down here. How do we add water? Well, those are our flow boundaries. And our flow boundaries are in essence just hydrographs. So we have, in this case, 5 hours on this one. I think we have 6 on the other. We have flow conditions up to a peak of about 175 cubic feet per second by hour 3 at this location. Okay, and this is a hydrograph. It's shortened and condensed from the real hydrograph, but you know, it's there to give us that idea. We have another one here because we've got, looks like 2 tributaries coming in here. And we really want to explore that existing conditions. What's happening in this model? Well, I've run this already. Let me shrink some of this down. We'll come into the 2D results and we'll take a look at the maximum water depth in this model. I want to just turn off the contours here. And we can kind of see now we have a color ramp of this area here. We've got some depths, almost 8 feet deep at the upstream of the head wall. But we have flow that occurs over the road and flows. And in this case, it's not flowing up to that other channel that I, assumed. It's flowing south. And it's flowing over, and we have some depths, roughly, a little over a foot in a small little pilot channel that appears to be flowing at the southern limits of this 2D result. And that's something that we really don't want, because in this case, as we looked at when I loaded the drawing file, we want to begin to put a new set of lanes going north just to the east of the existing road. So we're going to have to identify, what can we do about this in that new design conditions? Because we could probably coordinate sags and things like that, but this is a good arterial, and we want to make sure and maintain this at this flood event, because there's been a lot of upstream development here. We can always take a look at water elevations, and it's always nice to turn the contours here on at that, and we can kind of see really what our gradient is, what's going on as water flows over here. And it's pretty helpful in many cases. We can zoom in, and we can always add labels and the like through this the property dialog here. We can kind of look at all those. It's a little busy at this point, but we can see that type of information. So at this point, I want to develop my proposed conditions, and doing this, I've got my existing conditions model built. I want to then save this model as my proposed conditions, and in doing that, I want to consider a couple of elements. One, I have a proposed terrain surface, again, for my design engineer who's using Civil 3D. He's built his corridor. He's meshed everything together. There's a little fuzziness about what's going on between the divided highway, but it gives us something to begin to look at this culvert in this culvert position. So I'm going to swap my terrain files, import my land XML file again. I'm going to maintain those XPTIN files. They can be reused in different models and different elements. I'm going to add that second land use. So that northbound lanes, import that or draw that, digitize that again. I'm going to extend the culvert. Now, there's a couple ways we can do this. If we had X and Y coordinates of up and downstream, we could just re-import those 2 new locations into that proposed conditions model. Everything's good, because really what we're doing is tweaking and designing that pipe. Then we're going to look at, what happens when we go from a 2-foot to a 4-foot or maybe a 5-foot diameter culvert. And then we're going to begin to evaluate those conditions. how do we build scenarios? So when we look at proposed conditions in the scenario manager, we can add child scenarios. So we've got a base scenario. So that's going to be our extended culvert at the existing size. We're going to make a child scenario, and the only thing we're going to change in that child scenario is the diameter of the culvert. We could probably change slope and things like that, but in this case, I left all of the slopes the same, only changing the diameter for each one of those. And then we could run the scenario or the solve manager to perform each scenario individually, but doing that simultaneously. And in doing that, all three runs will run on an individual processor within our machine. Sure beats just hitting solve and waiting 10 minutes for the first run, waiting 10 more for the second, and waiting another 10. So that's a nice 30-minute, coffee break for each of those. We can run all of those within that time frame. They're maybe a little off, as you can see in the image there, but they work. Once we have that, we can use XP2D utilities, to do a difference. We'll take the existing conditions and say our 5-foot diameter scenario and prepare a difference between those two elevation models. We can load that directly in xpstorm and add all those different results files kind of on top of each other. It may get a little cluttered, but it gives you that ability to look at the results. And then we can export that map, again, using the XP2D utilities and looking for specific elements, whether that goes out to an a grid ASC file. We can do depth, we can do velocity, we can also do elevations. And from those that exported elevations, we can import and create a DEM surface back into our design applications to be used in either the profiles or the sections of that road to annotate what's going on. So let's switch over to XP again. Close out my existing model, and I have a final conditions complete model all ready to go. We'll let this load for a second, and we can kind of see in this location now I have my land use. I'm going to turn my roads off here. I have my new terrain. Kind of see the slopes on the new corridor within that. So I have this model. I also have my different scenarios. So if we look at the base scenario and take a look at the conduit profile, we can kind of see that I have a 2-foot diameter profile. I have a length of almost 400 feet comparatively to the 68 or 65 feet, if I recall correctly, of the original. And again, the only element different between each scenario is the diameter of the pipe. Okay? In doing that, I can take a look at my base scenario, perform my solve manager, which I won't run, and I can take a look again at the maximum water elevation for that model. As we can see, we probably have just as bad, if not a little worse, set of results. Okay, how do we take a look at what's going on with that? So we can go and we can add our existing conditions model very quickly by selecting our existing condition results from the XMDF file. It will turn off the results initially, so we'll look at the water elevations from the base scenario. And I want to compare that to, I guess, my pre-development condition. And I want to take a look at that file here. Okay, slight difference. It's a little tough to see, however. But we can kind of see that our proposed conditions, we have, a much larger extent going on. And we also have a condition that wasn't apparent initially, where it looks like maybe my grid isn't big enough. So that tells me that this scenario probably fails. Zoom back out. Well, let's go ahead and look at the 4-foot. Look at the 4-foot diameter scenario, and my results automatically just display. We no longer have flow over the road. And in fact, it looks to be all within the channels, both up and downstream. I'm assuming 5 will probably pass as well, but it changes our results. Upstream is a little lower, downstream is a little higher. Obviously, we're passing more water from up to down, and those seem to be the logical extents of that. So how do we determine how much, how different? Well, we go to our tools and we look at the XP2D utility interface. And selecting that, we actually have, and forgive me if I'm having a glitch with my video card. I am missing occasional tabs in xpstorm. There is an XP2D difference tab that is here that allows us to select one file. I'll go to the output, select the existing conditions, go to the input file, also using the default subdirectories, 2D results, output, and I can select my final condition calculation and select and name a file that will contain my differences. The calculations take about 3 minutes. As you can tell, it's a pretty large file. But what I want to do, let me remove my existing conditions. So I actually want to load those so I can see what those differences are. Come back to model, differences, and here's my comparison of existing and my final. And I can take a look at, here is my 5-foot diameter element. And then I can take a look at this difference file, and I'm going to do maximum depth. Because what that is telling me, because we compared the two elevations, the comparison of the two elevations is the depth. Had I selected max water elevation, we might not have seen anything. Actually, I'm pretty sure we wouldn't see anything. So we can kind of see where all the differences are. So upstream of this, there is a large difference in the level pool upstream of the road. Obviously, all of the water downstream of the road and overflowing the road is a big difference. Plus, we've also got a difference here within, really where we filled to build our new road. So we can see that, we can label those, and we can ultimately identify what's going on in there simply by interrogating the model right here within xpstorm. Now, one of the nice things, it's always nice to actually get the results not only here. I mean, this is visually, this communicates what it needs to do, but typically we need to submit this to other agencies, need to incorporate this into our construction plans. And in this case, we want to, again, utilize the tools XP2D and export the 2D results to GIS by selecting that same XMDF file for the scenario that we want to export. And we can change that to the Esri grid, and we can change that to the water level, and we can export that out. In this case, I want to export the maximum water elevation, and I do want to change the grid size to 3, which is 1/2 of the original grid. Okay, I don't want to get any finer than that because then I don't have results there. When we have a 6-foot grid, we have results at all the corners of that grid. So a 3x3 grid of my results is probably about as tight for a 6-foot grid as I really want to get. Okay, I can export that. And when I get back into Civil 3D, for example, I can create a digital elevation or a surface from a DEM file, and I can select that ASC file. And what that'll do is import all of the squares, subdivide each of those squares into triangles, and we can look at that directly on top of our existing ground surface. And now that's a 3D surface that can be used in cross sections, could be used in profiles, could be used for earthwork calculations or things like that. Maybe you have to prove, fill or something like that. Cutting compensatory, occasionally you'll have to do compensatory storage calculations, and this would provide that scenario to do that. Okay. You can always import this directly into a regular tin surface. A tin, this ASC file can be added to a tin surface. You'll get all the same triangles within here, but you won't get the boundary elements. So you'll have to do some trimming of the tins so that it doesn't cross this, cross the road here and any of the bends and things like that. You'll have to do some cleanup if you use a DEM within a regular Civil 3D tin. Okay, so that's kind of how we can use xpstorm to go from really existing conditions from our model, consider the impacts of not only the change in the length of a pipe, but the different diameters within the pipe, and begin to evaluate what the change of flooding is, both up and downstream of our model. So with that, I'll kind of turn this over to Nicole.
Thank you very much for joining us today. We hope you enjoyed the presentation. We look forward to the next time you get to join us, and we hope you have a wonderful day.